let's kick it off. Good morning, good afternoon, or good evening to everyone on this call, depending on which time zone is your home zone. I know we have people joining from all across the world, so welcome to the session, the DBA Masterclass Multitenant session today. Let me also say thanks a lot to Patrick Wheeler, because for him it's a very early morning, just 5 a.m. about. He will be your presenter for the day. And other than that, we have Dominic, Robert, Joseph, and myself here who will be supporting Patrick on the Q&A panel. So whenever you have questions during the session, use the Q&A button in Zoom, ask your question, and then one of us will provide you with an answer. For today's session, I quickly go and introduce to everyone the DBA Masterclass series. So for those of you for what this is the very first time to join the session, just to give you a quick introduction what this is about and what you will learn here. Then I will introduce you to the hands-on workshop that we provide as an addition to this series, supporting Patrick's presentation. And then I will hand it over to Patrick so that he can give you all the nuts and bolts about multi-tenant, pluggables and clones, etc., so that you learn a lot. And then we close it up with a Q&A session. Again, please ask your questions anytime. Use the Q&A button in Zoom, and we will try to answer them as quickly as possible. All right, so this Masterclass series, it's a long-running series already. It provides you a lot of learning opportunities about different technologies around the Oracle database. Great opportunity. Go to this website here on the webpage where you can find all the previous run sessions, which you can still access. And if you go for more than 6 sessions, I think you can even earn this little badge here and put it onto your shirt, which is a nice addition. So here's an overview of the past sessions. There's also another one coming in probably around November time. Check the webpage to see what will be the topic then for the next session. Next, I quickly want to introduce you to the Live Labs workshop platform that we provide and run here in Oracle, which is a platform where you can access hands-on workshops 24/7 for free. Check out the webpage. This is also the workshop that we are running, the workshop that we recommend as an addition to this session, which is all about multi-tenant and pluggables. And in order to access this one and get the best experience, it makes sense to sign up for an Oracle free tier account, unless you already have access to an Oracle tenancy. If you're registered to the session, you can get a tenant without providing a credit card whatsoever. Use the link here and sign up quickly and get your tenancy access. Once you have that, you can launch the hands-on workshop, the Live Labs workshop, by going to this to this web URL highlighted here on this deck. Just click on the launch free trial workshop, and then you're ready to go. You can enjoy a hands-on experience around the topics of pluggables, clones, containers, and the Oracle Multitenant topic. And now, without further ado, again, good morning, Patrick, to you across the Atlantic.
Good day to you.
And the show. I stopped sharing here.
Today's session is a DBA masterclass based on multi-tenant, and I'm the product manager of Multitenant. So bearing in mind it's about multi-tenant, we'll talk a lot about this, but it's a masterclass, which means that we'll go into some depth. But before, I'm going to review a little history, some of the major milestones in the history of multi-tenant. Multitenant was born on June the 23rd, 2013. It was a very proud day as we introduced to the family this new flagship option of Oracle database. It was 12c back then, released 12.101. And since then, it has matured rapidly, almost as if in doggy years. If you're a dog owner, you know, we sort of age dogs by sort of 7 dog years as equivalent to 1 human year. And it was about the same with multi-tenant. So release 12.2 represented grade school, if you like. It's a big step in an infant's life. And so it was for multi-tenant. We delivered some important online provisioning enhancements. I'll talk about some of those actually later on, along with support for software as a service use cases. And I wanted to talk about those, but we didn't have time today, maybe another session. With the launch of Oracle Database 18c, we had a high school graduate. Multitenant's backpack was crammed full of premium features, such as Snapshot Carousel and refreshable PDB switchover. And I will talk about those. Multitenant continued to overachieve at university, graduating summa cum laude. In 19c, all database features now work in a PDB, with no exception, and that's a big deal. We'll see why in just a sec. Multitenant's the foundation for autonomous database, and we've completed the massive upgrade of NetSuite with 24,000 tenants, each in their own PDB. And now with 21c, now available on both in the cloud and additional platforms, we have a responsible citizen of the world. Those are supposed to be little images of the world I drew here, different parts of the world. Yeah, from 21c onwards, this is the only architecture of Oracle database. So lots to be proud of there. And I wanted to pick out in this session a lot of the highlights, I think, and bearing in mind this is a masterclass. What I usually do with a multi-tenant overview is I cover the material in the next 2 slides in about 45 minutes, but now we're going to charge through it all. Oracle Multitenant delivers the full promise of the database cloud. And my phrase here is isolation and agility with economies of scale. I think that's what you want from a cloud database. Applications run unchanged in self-contained pluggable databases or PDBs. PDBs are simple to clone and to move to and around the cloud. A container database or a CDB consolidates many PDBs. You patch the CDB and you fix all the PDBs in it in a single stroke. That is operational efficiency. And the shared infrastructure model is highly efficient, so you can support more applications per server. And that is technical efficiency. So we deliver a 4-prong benefit proposition, value proposition. We minimize capital expenses because you can support more applications per server. We minimize operating expenses because you can manage many as one. We increase agility and provisioning and relocation and scaling, all sorts of things. And it's easy. It's easy to adopt because applications run unchanged, and it's easy to use because the interface is very simple. You already know how to use it. It's SQL. So as far as the overview is concerned, that's it. But this is a masterclass, so we're going to go a bit deeper. And these are the main topics I'm going to be talking about. We'll talk about database architectures, faster, easier upgrades. Now, provisioning has always been a strong suit of multi-tenant, and it keeps getting better. There are several enhancements to discuss in this category. Transportable backups eliminate an obstacle to portable pluggability. Mission-critical deployments demand data guard, and the integration of multi-tenant with data guard continues to strengthen. And again, when you talk about mission criticality and huge scalability, you have to be talking about real application clusters, and the integration there is extremely strong. So in parallel on the way through this session, we'll be doing Q&A using the Q&A feature of Zoom. So be sure to use the Q&A button and not the chat. Don't be shy. I see some people already in there. That's good. And we've got a team of experts standing by. So let's see, there's Kevin who spoke earlier. Thank you. Joe Burnens is also joining me from across the pond. Thank you, Joe, for getting up early to join this one. We have Robert Pastine, thank you. And we have a new hire to Oracle, Dom Giles, who joined, I believe it was last Monday. So it's just Dom's second week, just getting up to speed now. But Dom, thanks for joining us here as well. There's a little bit of a nudge and a wink to Dom. Many of you may know him already, and it's great to have you back, Dom. Okay, I showed you this phrase before, didn't I? I like it. Isolation and agility with economies of scale. That's the key thing, I think, for database architectures, particularly cloud database architectures. Now, whether it's OCI, another public cloud perhaps, or your private cloud, this is the way to go. Multi-tenant delivers on this promise. It's the architecture of the cloud. So let's go in and review a little history. Now in 19C, well, let's go even further back. The non-CDB architecture was deprecated back in 12.2. I think it was the summer of 2014. 19C was the last release with this non-CDB architecture. 19C, as you probably know, is our long-term support release. Now, the prerequisite for us replacing the non-CDB architecture is that all database features work within a PDB. In 19C, there's nothing you can do in a non-CDB that you can't do in a PDB. And of course, that's a very important thing. And from release 21C and beyond, multi-tenant is the only architecture of Oracle database. So here you are, you thought in the multi-tenant masterclass. In fact, you're in the Oracle database masterclass because this is the architecture now of Oracle database by definition. And in both releases, both 19C and 21C, up to 3 PDBs may be created per CDB without requiring the multi-tenant option license. I don't want to talk about licensing too much, but it is important to understand the difference between the architecture and the commercial licensing arrangement. 3 PDBs per CDB is acceptable without the license. Okay, now before I describe one of the key architectural innovations of multi-tenant, I want to review 2 important design goals. And the first one is portability. A pluggable database is a portable database, and relocation between CDBs has to be simple and fast. A relocated PDB carries with it lineage, a patch registry, encryption key information, and so much more. Okay, so design goal number 1, portability. Number 2, compatibility. So consider, for example, an application connected to an Oracle database in the old non-CDB architecture. Now, our compatibility goal is expressed by what we call the PDB non-CDB compatibility guarantee, which is that you cannot tell from the viewpoint of a connected client if you're talking to a PDB or a non-CDB. And people laugh at me when I say this, but it's a very important principle. If we get this right, which we have, it means that the application will run unchanged in a PDB. Even if it refers to data in a remote database, it'll do this by means of a database link. Now we upgrade this all to the multi-tenant architecture, and everything works as before, even the reference to the remote database. We resisted the temptation to change to a 4-part naming scheme. So this makes the adoption of this architecture very easy. Application changes are not required. Now, I'm going to introduce a major architectural innovation that allows us to deliver on both of these design goals. Let's think about what happens in a traditional Oracle database over time. When we set up a so-called empty database, it's not really empty at all. By definition, a relational database includes what's known as a metadata dictionary in which its own structure is defined. So a brand new Oracle database comes with the Oracle Data Dictionary pre-populated with the database's own structural definitions. But that's not what the database is for. You installed it to support some sort of application. So I think of this great divide between the application data in the pink side there, or the user data over on the left. Sorry, so the application data, the user data in the pink, and the metadata on the other side. So as you define this application and begin to use it, we begin to populate the user data side of the great divide. But the metadata which defines the application, its tables, columns, indexes, functional logic, all that stuff, is stored in the metadata dictionary alongside the definitions of the tables and columns and indexes and functional logic of the Oracle database itself. Now, in the old architecture, they all were, all mixed up together. If you do a query on the data dictionary, it'll typically return rows from both the Oracle supplied metadata and the metadata for the user system. And that's been absolutely fine for all these years, but it's an obstacle to our new goal of portability. If you want to move this application from one database to another, you'd have to unpick it row by row from the origin and reinstall it all in the destination. And row by row means slow by slow, to borrow a phrase from our old friend Tom Kite. Now, to address this requirement, a major innovation of the multi-tenant architecture is what we call the horizontal partitioning of the data dictionary. We literally create this second copy of the data dictionary in what we call the pluggable database, or the PDB pluggable database. Conceptually, this contains just the definition of the application. The other copy of the data dictionary lives in what we call the root, down at the bottom here. And at a high level, this stores just the Oracle supplied metadata. So how well have we delivered on our design goals? It's pretty clear that we've solved the portability problem. With both application data and application definition encapsulated in the self-contained pluggable database, we can simply move this to another route. But what about the compatibility goal? Now, again, it's pretty obvious that an application query, say joining emp and dept, in this example is just going to work unchanged. But what about the experience of a DBA? In the prior architecture, a DBA would expect to perform a query against the metadata dictionary and return both the data defining the application structure and the definition of objects supplied within the Oracle database itself. The problem now is that I've just told you that we've separated these into two different data sets. The solution is that we store in the PDB's data dictionary what we call stubs. And these stubs are references to the full definitions of objects that are stored in the Oracle data dictionary. For example, there would be a stub entry in the PDB's data dictionary for our famous package DBMS SQL. And it basically says DBMS SQL, full definition is down there. Now, what happens when a DBA queries against the PDB's data dictionary is effectively a union of the data in the PDB's dictionary itself, and via these stubs, via the definitions of the Oracle supplied objects in the root data dictionary. And this is how we deliver on the PDB non-CDB compatibility guarantee. Okay. Now, from day one, multi-tenant has helped us speed up upgrades. And this continues in 19C and 21C with some important enhancements that give upgrades an extra turbo charge. There's a brand new upgrade infrastructure in 21C. We further optimized the conversion of non-CDBs to PDBs. And we now automatically apply upgrades when opening a PDB in a higher version CDB. And in this section, I'll describe each of these topics in some depth. I'll start with the new upgrade infrastructure, what we call replay upgrades, and you'll see why. But to understand this new approach, I need to go into some detail about how a traditional database upgrade works. If you're reasonably familiar with database upgrades, as I expect you are, you'll know that this is a very flexible and resilient process. Now, we don't deserve any sympathy and we don't ask for any, but if you think about it, this flexibility makes this quite a challenging problem. And this is why I have such great respect for our upgrade development team. And for 21C, for example, we support upgrades in a single step from the previous version of Oracle Database, 19C. And we also support upgrades from 18C and from 12.2. So two basic options are available to the upgrade team. Either they could maintain separate upgrade scripts for each supported upgrade path. What a nightmare. Or they could maintain a single upgrade script that is applicable to all upgrade paths and is resilient enough to detect that some of the upgrade process may not apply. It's important that the upgrade does not fail when it encounters such a step. And it's this second approach that we have taken. This slide shows a simplified view of this. The first two columns of the table show, for the purposes of illustration, the sort of steps that might be involved in a typical upgrade. Across the top in the gray bar, we see various upgrade paths, versions from which upgrades to 21C are supported. And the last three columns show with check marks or X's whether each step applies to a specific upgrade from that version. So the individual upgrade steps here are just for illustrative purposes. For example, in step 1, create table DBA dollar something or other was introduced in upgrades from 12.2. So that needs a check mark in the 12.2 column. However, it was already present in 18C, so upgrades from 18C and 19C do not require this step. Similarly, looking at step 6, here we're dropping an index. Presumably this was introduced in 19C, so upgrades from 12.2 and 18C do not require this step. However, it is applicable to upgrades from 19C. So with this in mind, we can see that in general, any upgrade execution is going to involve some steps which are effectively no ops, nothing happens, no op, no operation, because they do not apply to that upgrade path. And this is how the upgrade is written to be very resilient. However, there is a slight performance cost for each of these no ops. Individually, each no op is pretty cheap, but cumulatively, the cost can be quite significant. In this simplistic illustration, we're only showing 10 steps. Of these, between 5 and 7 are no ops, depending on the upgrade path. And that's not a big deal. Realistically, though, a typical upgrade can involve many thousands of steps, and the aggregate cost of all of these no ops is quite significant. So the new upgrade infrastructure, introduced with Oracle Database 21C, improves performance by eliminating no ops from the upgrade path. Here's how it works. At a high level, we utilize the capture replay mechanism that we introduced in 12.2 for application container upgrades. This includes a repository of the various steps involved in the upgrade of an application. Now, this new upgrade infrastructure for the database itself utilizes the same mechanism for database upgrades. As part of database development, we run each supported upgrade path using the traditional upgrade scripts and capture in this repository all the effective steps in that upgrade path. The various no ops are not captured, and the result is a separate upgrade procedure captured in the repository for each supported upgrade path, all generated from the same familiar, resilient upgrade script that already works so efficiently. For example, referring back to the table illustrating a sample of 10 upgrade scripts in the virtual and the various upgrade paths to which each applies, we see that only 3 of those steps are captured for the upgrade from 18C, and 5 apply to upgrades from 19C. Pretty cool. Incidentally, we've been using this mechanism for several years in Autonomous Database for upgrades since 18C. So this new upgrade infrastructure enables fully automated upgrade operations when a PDB is first opened after it's been moved to a higher version CDB. And we introduced these new capabilities with release 21C. So this is summarized in the following table. There are 2 parts to this. We can use the capture replay mechanism to restrict upgrade procedures to only effective steps and automatically upgrade PDBs following a plugin if necessary. Okay. So this avoids leaving older PDBs in upgrade mode following relocation to a newer version CDB. And it's new in 21C. So if you relocate a PDB to a higher version CDB, so there's a typo here, higher version CDB, the PDB upgrades automatically when it's opened. And the same is true when you plug in a non-CDB. It's automatically converted to a PDB and upgraded if necessary when opened. It's faster because only the steps relevant to the upgrade path are involved. expensive, irrelevant, no ops are eliminated. And this is proven in Autonomous Database. It's a nice and easy upgrade on open. Now, the next topic here is conversion of a non-CDB to a PDB. And this is relatively straightforward and fast. But as a general rule, you can never be fast enough in computing, and we continue to invest to speed this up. Now, elsewhere, previously, I just explained this fundamental component of the multi-tenant architecture, the horizontal partitioning of the data dictionary. With that in mind, let's consider what happens when we adopt a non-CDB as a PDB. Now, basically, this involves plugging in this non-CDB into an existing CDB root. Now, the incoming former non-CDB knows nothing about this partition data dictionary. It grew up in the old architecture where all that metadata was intermingled. So initially, its data dictionary includes a full copy of the Oracle supplied metadata. This needs to be replaced with the stubs I described earlier. Now, it's the script non-CDB to PDB that performs this. After this is run, we have the desired horizontally partitioned data dictionary. Now, none of this is new in 21C or 19C for that matter. What's new is the faster, easier part. In general, things run faster because we've eliminated unnecessary invalidation of customer-defined objects. We needed to focus only conversion of Oracle objects. Customer objects need not be impacted. And this means that the conversion timing is going to be more consistent, regardless of the number of objects in the non-CDB. Furthermore, the effective steps in non-CDB to PDB.SQL are now captured in the new upgrade infrastructure I just described. And this means that this conversion can now happen automatically on PDB Open, as with other upgrades when you're moving to 21C. Okay, time to move on to another big topic, provisioning. And this has always been a strong suit of multi-tenant, and it just keeps getting better. There's a lot to discuss in this category. First, I want to be sure that you understand what happens behind the scenes during a hot clone. And this is important background information for various enhancements that we have that we'll cover in the next few sections. So I want to get that background nailed down. Then we'll move on, talk about faster and easier encryption and decryption operations, what I call precision cloning with a snapshot carousel, and snapshot clones on ACFS. Not all sparse file systems are created equal, as we shall soon see. But first, let's explore the inner workings of cloning. And I need to start at the beginning with what's involved in a cold clone from a technical perspective. Now, a cold clone is a relatively simple operation to understand. The source PDB must be in a quiescent state, hence the term cold clone. Basically, you close it and reopen it read-only. In this state, there are no incomplete transactions, and all the blocks are flushed to disk. So performing a cold clone is therefore simply a matter of scanning all the blocks of the source and copying them over to the target. Even this is a sophisticated operation, however, as parallel execution servers will automatically be invoked to optimize the performance. This is why cloning happens so fast. Once the clone is complete, the source PDB can be reopened read-write so that processing can resume. So we can do cold clones. Why not just do hot clones? It's easier said than done, and I'll explain why. Before we get into that, let's talk about what happens in a database which is open read-write. And here I'm going to use color coding to show the passage of time, as illustrated by the clock in the upper left-hand corner. So in the first interval, what we could think of as yellow time, we see some data changes in blocks scattered through the data files on disk. Corresponding to this, we have undo segments in the undo table space, and of course, redo segments written to the redo log file. Each of these changes is color-coded according to the time interval, in this case, yellow. Notice that some of these changes, data file blocks, undo and redo, have check marks in them. And these indicate that the change is associated with a committed transaction. So now as we move into brown time, we see more changes. Notice that one of these changes is to commit a transaction which began in yellow time. And all of this is summarized in the legend here on the right-hand side. And we can now watch the database activity proceed as we progress through this sort of slate color. Steel, I think, is next. Here we are. And perhaps charcoal time. The point of all this is that in general, we must assume that this sort of activity is going on in a database which is open read-write. That is, that transactions are changing data blocks scattered throughout the data files, and it's not reasonable to assume that at any time there are no uncommitted transactions. So hot cloning has to take account of all this activity. With all these changes going on, it's hard enough to guarantee that the clone be physically consistent with the source. But what's required is that it be transactionally consistent with the source as well. So incidentally, this is why it's very important not to rely on storage level replication technologies alone to clone your databases. If you do so, the operation will appear to complete successfully. However, there are likely to be some transactional inconsistencies. Now that we understand the challenges to be addressed by an online, that is a hot clone, let's see how it works. And again, we'll use the same color coding to illustrate the passage of time. So we begin the online cloning operation in yellow time. And as with the cold clone, we do parallel scan of the data files. In this illustration, during yellow time, we scan the first two rows of blocks, if you like, and these are read and copied over to the target. And so far, everything is okay. All changes made to blocks in the source that we've scanned so far are copied over to the target. Now, as we run into brown time, we scan the next set of blocks. And again, there are some changes made in brown time that are picked up by this scan and copied over to the target. However, there are also some changes made to blocks which were previously scanned. And these changes are therefore not reflected in the target. Now, as we proceed through slate, steel, and charcoal time intervals, as before, we see that some of the changes made in the source during the cloning operation are reflected in the target. However, some changes made to the source during the cloning operation happened after those blocks were scanned, and those changes are not reflected in the target. So here we see, in these little red things, the blocks in the target, which the corresponding block in the source has been changed, but that change is not reflected in the target. So if I toggle back and forth, you might just see that there. So far then, we've copied all the blocks from the source to the target, but because the source was changing while the blocks were being scanned, what we might refer to as a fuzzy read, the target is not physically consistent with the source. So the next step is to fix that. And that's done by copying over all this redo that has accumulated since the clone operation began, scanning that and applying all those changes on the target. And the result of that is a physically consistent clone on the target. However, note that not all the transactions in this physically consistent clone are committed. And it's now necessary to roll back any uncommitted transactions. And this is done by applying the undo corresponding to these uncommitted transactions. So when this is complete, the clone is in a transactionally consistent state. So the relevance of all this from a high availability perspective, of course, is that hot clones allow cloning operations to be performed whenever necessary without incurring an outage in the source system. Okay, so file that away because it becomes relevant a little bit later on. But I mention it here under the topic of provisioning. So now we're going to move on a little bit and talk about encryption and decryption operations. Now, in general, no single technology is sufficient to provide comprehensive security. And Oracle's security philosophy is defense in depth. What's required is a suite of complementary security technologies to protect against a very broad range of threats. Prominent among these is transparent data encryption, or TDE. With multi-tenant, each PDB can have its own encryption key. Now, a typical requirement is to encrypt an unencrypted PDB as it's migrated to the cloud. Remember, there are lots of options in Oracle Cloud, but security is not one of them. PDBs must be encrypted in OCI. So for this reason, rekey is the default mode. However, on rare occasions, in non-OCI deployments perhaps, the DBA may choose not to encrypt the PDB. If no encryption is required, you just say no key. From a security perspective, it's a good practice to rekey PDBs periodically. However, historically, this could involve downtime, which of course may impact operational availability. With this new capability, these operations are now possible with near zero downtime. So that's a pretty big deal. So rekey default mode. Again, if you don't need encryption, you just say no key. Next topic is snapshot cloning. And again, in each of these themes, I want to sort of go back to the basics so you understand the underlying principles. So one of the basic concepts here behind storage efficient clones is to do with copying files. And what is a file? It's a collection of data blocks and headers. Now, a basic copy operation duplicates both the data blocks and the file headers. Effective and simple, but it's expensive too. Now, this is rethought with copy on write. In many situations, the two file copies are only expected to differ slightly. In these cases, it's inefficient to create these full copy clones. Where the two files are expected to be substantially similar, copy on write technologies can be far more efficient, and the approach is illustrated here. So again, the file's a collection of blocks and headers, and to create what is apparently a full dataset copy of the file, all that's required is to copy the header. This copy is typically implemented with a sparse file and points to exactly the same data blocks. It's only when a change is made to one of these files that the affected block or blocks are copied and changed. The file header for the changed file continues to point to the unchanged blocks it has in common with the source file. However, references to the affected blocks are updated to point to the changed block copies. So this is why this technique is known as copy on write. And this is the fundamental technology that underpins snapshot cloning in multi-tenant. Excuse me. However, various storage technologies differ in subtle ways that have important implications for how snapshot cloning behaves. Now, a seemingly subtle example here is whether the snapshot is taken at the file system level, at the file level. So first, let's consider a file system-based snapshot. So here we've got a single file system for an entire CDB. And here we're going to walk through some typical lifecycle operations. So as I do so, pay attention to this column on the right-hand side here that shows the aggregate storage assigned to PDBs in this CDB. So we'll start by creating the first PDB, red. Let's assume it consumes 10 gigabytes. So the total storage for the PDB is now 10 gigs. Now we create PDB green, another 10 giga, and PDB gold. So each of these consumes 10 gigs. So of course, our total storage is now 30 gigs here on the right-hand side. Now, we're going to drop PDB green. Guess what? Storage goes down to 20 gigs. It all seems very obvious. But now things get interesting, so pay attention. Now I'm going to create a snapshot copy of PDB red. But because this is a storage efficient clone, it will require negligible additional storage. So although it's apparently a full dataset copy of PDB red, under the covers we're using that copy on write technology I just talked about, and therefore the overall PDB storage is essentially unchanged at 20 gigs. And this is outstanding. What appears to be a full dataset copy requires negligible incremental storage, and therefore very little is required, very little I/O is required, and the operation completes very quickly, even for substantial PDBs. Now at the bottom left, we can see the file system snapshot that supports this clone. So far, so good. But now we'll see how things can go wrong. Watch carefully. Now I'm going to drop PDB gold. But notice the storage remains at 20 gigs. What's going on here? So I've dropped PDB gold, and I'd expect that its storage, that 10 gigs, would be released as a result. But because this file system snapshot that enabled the snapshot clone of an apparently unrelated PDB red, that storage is held hostage by this file system snapshot, and it cannot be released. So it turns out then that these apparently unrelated PDBs have a dependency in the file system. So you can imagine how it might be possible actually to consume more storage, not less, when using snapshot cloning than with regular cloning, if there's a lot of creation and dropping of PDBs going on and in an environment where snapshot cloning is also taking place. So clearly this is an undesirable outcome. And the workaround is to have different file systems within the CDB. Now let's move on to consider the same example where snapshots are taken at the individual file level. And this is how the Oracle ASM cluster file system, ACFS, works. So we'll start by creating our 3 PDBs, red and green and gold. As expected, our total storage by PDBs is now 30 gigs. And again, there are no surprises when we drop PDB green. Its 10 gigabytes are released, and now we're down to 20 gigabytes. ACFS supports snapshot cloning, of course, and so when we create the snapshot clone for red, there is insignificant growth in storage. Looking into the storage layer, we now see only the sparse files associated with PDB red. That's all that's required to implement the snapshot clone. This is the file level snapshot. Now, importantly, because it doesn't involve the data files for any other PDB, when we drop PDB gold, we see the storage drop down to 10 gigs, as expected, because it's released here from the storage layer. So it's a subtle difference, but an important one. All right. So in this slide, I try and summarize this and other important capabilities across various different storage technologies. For each type of storage listed on the left-hand side, we see how snapshots are enabled, whether clone sources are read-writable or read-only, whether snapshots are taken at the file level or the file system level, as we've just discussed, and whether split mirror cloning is possible. So without reading the slide out for you, we see that ACFS has ideal characteristics. It supports snapshot clones natively. The clone source remains read-writable, which is important for Snapshot Carousel. We'll talk about that in a minute. And that snapshots are taken at the file level, so storage is not held hostage when dropping apparently independent PDBs. Now we can move on to discuss precision cloning with Snapshot Carousel. But first, I need to tell you about the Snapshot Carousel. And this was introduced with 18C, but we've enhanced it a couple of times in the last release or two. Now, the Snapshot Carousel is a repository for point-in-time copies of a PDB. For example, we might take nightly snapshots of a particular PDB. Now, it makes sense to limit the number of historical snapshots we take. Perhaps we only need snapshots for the past week. The maximum number of snapshots to be retained is configurable, and the default is 8, which happens also to be the highest value that's currently supported. Now, every 24 hours at midnight, we drop the oldest snapshot. You can think in terms of the carousel rotating by one slot. The newly vacated slot now becomes the slot for T0. A fresh snapshot is taken, and this is dropped into the slot for T0. And the process repeats the following midnight as the calendar flips from Tuesday to Wednesday. And again from Wednesday to Thursday. And Thursday to Friday. So the snapshot carousel can be very helpful for debugging date-specific problems. For example, we might have a problem reported on Friday. It's a new problem, which seems to be data-related and arose earlier in the week. However, the report is not specific about the exact date on which it was first encountered. So you might try a bracketing approach. You take clones from the snapshots from Monday and Tuesday and Wednesday and run tests to see whether the problem shows up. Now, the problem was not reproducible on Monday, so we eliminate that date. And further testing shows that the problem shows up already on Tuesday. So we can eliminate Wednesday too, and now drill in to Tuesday in more depth. And you'll notice how agile this process can be. These are the sorts of capabilities that modern cloud-based development organizations require, so they can keep up with the demands of the modern business climate. Now, typically snapshots can be materialized either as full copy clones or as snapshot or thin provision clones, as we've just seen. Now, another great use case for the snapshot carousel is as a convenient source for simple point-in-time recovery of a PDB. Let's say a few days go by uneventfully, business proceeds smoothly, and snapshots are taken automatically every midnight. But then, on Wednesday the 28th, we discover that a serious data error was introduced the previous day, Tuesday. It's determined that the simplest remedy, is to recover from Monday's snapshot taken before the data error was introduced. So we simply drop the current PDB and restore a clone of Monday's snapshot before the data error was retrieved. Now, a further enhancement to Snapshot Carousel, and this one's available with 21C, is precision cloning as of a specific timestamp or an SCN. Now, in this illustration, let's say again, snapshots are taken daily at 2 a.m. and our intention is to recover to 7:26 and 41 seconds on Tuesday, October 5th, 2021. Here's the syntax. Create pluggable database, red, from gold, using snapshot from Tuesday at timestamp. Nice and easy. Let's see what happens behind the scenes. So We clone the specified snapshot. So in this case, the one that we took at 2 a.m. that morning, and then we roll forward to the required timestamp using the archive logs. So using this very familiar syntax, it's also possible to specify the recovery point in terms of an SCN instead of a timestamp. Pretty cool, and the Snapshot Carousel enables all that. Okay, next big theme, another important enhancement is transportable backups. Now, a sound backup strategy is, of course, a fundamental element of any high availability system. And a very basic backup strategy is to take periodic full backups. Perhaps you do this every Sunday at 2 a.m. Well, at least you've got a backup, but it's a pretty primitive strategy. In the event of failure, the recovery point, RPO, would therefore be the previous Sunday at 2 a.m. Okay, weekly full backups combined with retained archive logs enable point-in-time recovery, sometimes called PITR, P-I-T-R, to any time during the week. That's far better RPO than is achieved by just the weekly full backups alone. However, the recovery through several days' worth of archive logs can be quite a lengthy procedure, and therefore the recovery time objective, the RTO, is in general relatively poor with this strategy. So with good RPO, but poor RTO, we might pronounce this strategy as tolerable. Now, an established best practice with RMAN-based backups is shown here. We have periodic full backups with regular incremental backups taken at intervals in between. So a typical model is you take weekly full backups, perhaps Sunday at 2 a.m., and then daily incrementals, perhaps 2 a.m. every other day of the week. And archive logging is also enabled. And this is indeed a very respectable strategy. It delivers good RPO, since the point-in-time recovery to any point in time is possible, and it delivers good RTO, since restoring from a full backup, then applying the required incrementals, and then recovering with archive logs to the required point in time is a very efficient strategy. So this slide illustrates a point-in-time recovery. And in this example, we're using a typical backup strategy involving these full backups, these weekly full and daily incremental backups. And let's say that at lunchtime on Thursday, we decide to recover to 10 a.m. on Tuesday. And that's what you tell RMAN to do. What RMAN does behind the scenes is it restores the previous Sunday's full backup. It applies the incrementals from Monday and Tuesday, and it uses the archive logs to recover from Tuesday at 2 a.m. till Tuesday at 10 a.m. So far, so good. But what happens if the PDB that I'm recovering has been moved between CDBs, between Sundays, since Sunday's full backup? For example, this might have happened, let's say noon on Monday. And here I provide a bit of historical context because I'm sure many of you have been using multi-tenant for a long time. So it's far more relevant for those with experience of these prior releases of multi-tenant, but may also be of interest if you're looking at multi-tenant just for the first time. Now, in prior releases, to achieve the same point in time recovery, that is at lunchtime on Thursday, we decide we want to recover to 10 a.m. on Tuesday. The PITR was still possible, the PITR was still possible, but it was more complicated. You had to restore an auxiliary instance. You had to recover to a point before the unplug. You had to manually move the data files to the new PDB. You had to roll it forward to the desired point in time. So in practice, this additional complexity could limit the agility of moving PDBs between CDBs in prior releases of Oracle database. So the transportable backup feature, which is now available, I think certainly since 19C, eliminates all of these additional complexities. And associated with a point-in-time recovery in a situation when the PDB in question has been moved between CDBs since the last full backup. So the point is, with transportable backups, you can perform a PDB PITR to a time after the PDB has been moved, but before the next full backup. And this works whether the PDB has been moved via unplug plug or online relocation. So good stuff. Okay, in this section, I'll discuss considerations for provisioning PDBs in high availability configurations protected by DataGuard. Now, two familiar technologies cover both extremes in terms of data replication. At one extreme, we've got DataGuard, or preferably active DataGuard, which can be configured at the CDB level. And this is a great example of managing many as one, and thus reducing operating costs. Configure this once at the CDB level, and active DataGuard will replicate the transactions from the primary to the standby for all the PDBs in a single stream. Granular control is possible to the extent that a PDB can be configured with no standby where appropriate. At the other extreme, for replication of data at the individual PDB, Golden Gate is the perfect choice. With Golden Gate, it's possible to have bidirectional replication between CDBs, as is shown here. And this can even be used in an active-active configuration, which is a key capability for supporting a truly zero downtime upgrade. Now, important considerations apply to certain forms of PDB creation in DataGuard configurations. And two of the most common provisioning operations, creating a PDB from seed and creating a local cold clone, work absolutely fine with DataGuard. Now, let's walk through an illustration of this to understand what's going on. Here we see a high availability configuration with a primary CDB on the top and a standby CDB at the bottom, with replication managed by DataGuard. And we begin with a new CDB with no customer created PDBs, only PDB $seed is present in this initial state. And when we create a new PDB from seed, the create PDB operation replays successfully on the standby. And this is possible because PDB $seed, including its data files, is already present on the standby. So the new PDB is created successfully on both the primary and the standby. Similarly, a local cold clone, that's a clone of a PDB already present in the primary and open read-only, will succeed and replay successfully on the standby because it is already present in the standby, including all the data files necessary to process the operation. However, for various reasons, some other provisioning operations are more complicated. For example, a hot clone, that is a clone of a PDB performed while the source PDB remains online, in other words, open read write, is complicated by the fact that there are two recovery operations involved at the same time. Think back to what I was saying about how hot cloning works, right? That roll forward and roll back, that's a recovery operation. So we've got two of them happening at the same time. There's the MRP, this recovery to do with the hot clone, and the MRP here to do with DataGuard. So one of these is to ensure that the hot clone itself is transactionally consistent. The other in DataGuard, as I say, and these two recovery operations could interfere with each other. And to avoid that, the hot clone to a DataGuard primary must have no standby replica. So this can be viewed as the functional equivalent to including the clause standbys equals none in the hot cloning operation to this primary. So for the purposes of this discussion, a remote cold clone that is a cold clone of a PDB in another CDB, is comparable to the plugin of an unplugged PDB. In both cases, unlike creating a new PDB from seed or performing a local cold clone, by definition, the data files for the newly created PDB are not already on the CDB, on the CDB. Therefore, the complication in these cases is that not only do we need to copy the data files for the new PDB into the primary CDB, we also need to copy them onto the remote CDB. Okay, with these considerations in mind, we introduce some special procedures to ensure the smooth provisioning of PDBs in DataGuard configurations. These involve some additional one-time steps in the process of setting up the DataGuard environment and a simple procedure to follow in each of these somewhat more complicated provisioning cases. So let's discuss the additional one-time steps involved in DataGuard setup. So we start by creating a self-referencing database link on the primary. This replays successfully on the standby to create a database link referencing the primary. Next, we set a parameter on the standby. This is named standby PDB source file DB link, and it should reference the database link created in the previous step. Now, finally, CDB root in the standby should be opened read-only. And note that no active DataGuard license is required if only CDB root is opened read-only on the standby. So this allows DataGuard to read the value of the parameter just specified. When a create PDB operation is replayed on the standby, it works just fine. So now we introduce a new simple procedure for employing what we refer to as the transient no standby PDB. So following this procedure ensures that even these relatively complex provisioning operations can be achieved in a few trivial steps. For example, let's say that our intention is to plug in an unplugged PDB or to perform a remote clone. We want this new PDB to be named PDB3. Now we start by creating what is referred to as this transient no standbys PDB. To do this, you simply include the clause standbys equals none in the create pluggable database statement. And the result of this is that on the standby, the transient PDB will be visible in mounted state, but its data files will show as offline. Next, we create the desired PDB, PDB3, as a local cold clone of the transient no standbys PDB. This replays successfully on the standby by copying the PDB's data files across the database link identified by the parameter standby PDB source file DB link. And now the transient no standby PDB can be dropped. So what seemed to be a relatively complicated procedure is reduced to this simple 1, 2, 3. And you follow this simple 1, 2, 3 procedure for hot clones in a high availability configuration protected by DataGuard. As before, the first step is to create the transient no standbys PDB, this time as a hot clone. Again, it's important to include the standbys equals none clause in the create pluggable database statement. Remember, the intention of a hot clone is to take the clone while the source remains online. Of course, this is consistent with our high availability theme, and clearly this requirement is met in this case, so the source stays online here. Next, we create the desired PDB, PDB4, as a local cold clone of the transient no standbys PDB. And this replays successfully on the standby by copying the PDB's data files across the database link, identified by that parameter standby PDB source file DB link. and the transient no standby PDB may now be dropped. So again, as you see, the same simple procedure, employing the transient no standby PDB technique is very useful for provisioning operations in environments protected by DataGuard. Now, in 21C, we introduce a new mode to DataGuard, which we call recovery isolation mode. And I'll show you how it works. Here we have an active DataGuard environment with the primary CDB on the top and the standby CDB on the bottom. And we see the so-called media recovery process, the MRP, replicating transactions from the primary to the standby. When we provision PDB red in the primary as a hot clone of green, an isolated media recovery process is spawned to avoid that conflict I was talking about just now. So this ensures that the MRP associated with instantiating the new PDB and its corresponding standby does not interfere with the main MRP. Once the new PDB and its standby are fully instantiated, the main MRP can take over. So this simplifies, this removes some of the cases where you needed to use the transient no standbys PDB technique in 21C. Okay, so now I'm going to move on to refreshable PDB switchover. This allows extremely simple management of per PDB replicas. The refreshable PDB switchover capability allows us to define replicas on a per PDB basis with only 2 CDBs to manage. So we might start by creating a PDB named red in CDB1, and then simply creating a replica of this in CDB2 using the familiar refreshable PDB syntax. We might add a few more PDBs, green in CDB2, gold in CDB1, and gray in CDB2. No replicas are required for green and gold, but we want one for gray. And as simply as that, we have 2 pairs of replicas being refreshed in opposite directions between these 2 CDBs. So now we come to the refreshable PDB switchover capability. There are several ways in which this can be very useful. For example, planned switchovers can be very helpful for load balancing. These resource meters show how busy things are. So the role transition is executed as follows. You connect to the current primary. I'll replay that. You connect to the current primary, and you might find it helpful to think in terms of connecting to the future replica. And you issue the statement, alter pluggable database gray, refresh mode every 2 minutes or something nice and frequent. From gray at database link, switch over. The syntax to set up the refreshable clone is familiar. And here I introduce the keyword switchover. User connections will now be to the primary, which is now in CDB1. And in this example, we've seen how trivial it is to perform load balancing with this capability while maintaining a replica on a remote server just in case. Now, in situations where the primary PDB fails for some reason, we can switch over to the replica and resume operations there. And we'd refer to this as an unplanned switchover. The 3 steps to perform the role transition from replica to new primary are as follows. You perform 1 more refresh of the replica. Remember that although the source PDB is no longer available, the refresh process involves reading redo from the primary CDB's redo stream, the online redo log and the archive redo log files. So for the purposes of this discussion, we assume that it's just the source CDB, including its redo stream, is intact, and it's the failure that the failure is confined to just the PDB alone. So therefore, it's reasonable to assume that the final refresh will succeed. What it achieves is to transport and apply any transactions that were performed against the primary between the previous refresh and the PDB's failure. After the surviving replica, alter the surviving replica so that it is no longer a refreshable PDB. And then open the former replica read-write, so that it can be used as the new primary. Now, let's consider the high availability implications of this capability. So in the sense that it can be used to maintain a replica in another server, we've seen how a refreshable PDB may be used as a replica on which operations may be resumed, whether the switchover is planned or an unplanned event, as we've just discussed. In that sense, it's worthwhile to consider the characteristics of a switchover from the point of view of recovery time objectives, RTOs, and recovery point objectives, RPOs. Recovery time objectives consider how long it takes before operations can resume in the event of a switchover. In other words, how long is the outage? The point is that RTO is affected by the amount of redo to be applied. In turn, this is a function of the rate of redo generation in the source PDB and the frequency of refresh of the replica. The worst case is a failure of the source just before the next refresh was to have occurred, assuming a relatively steady rate of redo generation at the source. The situation is likely to result in the maximum amount of redo to be applied on the replica before the switchover can be completed. So in general, a relatively high frequency of refreshes of the order of every couple of minutes rather than every few hours is likely to leave relatively little redo to be applied before a switchover can be completed. It's important to test thoroughly with realistic transaction volumes to ensure the process of refreshing the replica can keep up with the rate of redo generation. Now, recovery point objectives, or RPOs, apply to how much data is lost in the event of failure of the primary. In many cases, the failure of the source PDB alone will not cause any data loss. As long as the source CDB remains operational, all committed transactions should be protected in the online redo logs and archive logs of the source. It's therefore likely that even transactions that had not been applied to the replica at the time of failure of the source PDB can be recovered and applied to the replica before switching over to that. But the worst case is a total failure of the source CDB or its host server. In this case, the online redo logs and potentially even the archive logs on that server are inaccessible. With the basic refreshable PDB capability that I've described so far, there is in this and similar situations the possibility that all transactions that happened on the source since the last refresh will be lost. For example, if the refreshable PDB had been created with a statement, create pluggable database, myPDB from myPDB at DB link, refresh mode every 2 minutes, the maximum data loss is 2 minutes of transactions, assuming the refreshers have been able to keep up with the rate of generation of redo from the source. However, another strategy exists through integration with a DataGuard remote redo repository, which is a component of DataGuard FastSync. And this possibility arises because the refreshable PDB can read data either over a database link from the online and archive redo logs on the primary. This is what we've seen so far, or from a remote redo repository maintained via DataGuard's redo transport. This slide illustrates how this works. Here, DataGuard is the only component involved in scanning redo logs on the primary and transporting them to a remote redo repository. Having defined the refreshable PDB as before, we now modify it. to be refreshed from the remote redo repository. Now, this second option has several important advantages. It minimizes the impact of scanning redo logs on the primary. It minimizes the amount of redo transport between CDBs. It enables near zero data loss in a failover situation. Now, it may seem paradoxical, but high availability and disaster recovery are not necessarily the same thing. Let me explain. As discussed earlier, online PDB relocation allows a PDB to be moved between servers without taking an outage in the CDB. However, we've also seen that moving a PDB into a CDB protected by DataGuard can be complicated because we also need to consider setting up the corresponding replica in the standby CDB. Now, we could relocate the PDB into the DataGuard primary with standbys equals none. But then by definition, there would be no standby PDB. So in this case, we'd have high availability relocation, but a vulnerability from a disaster recovery perspective. Now, on the other hand, the transient no standbys PDB technique can be used to set up that replica, thereby ensuring that we have DR, disaster recovery. However, since this technique involves cold cloning, it is not a high availability operation. Therefore, in this case, we have DR, but not HA. And we want our cake and eat it. So to resolve this dilemma, we can use refreshable PDBs. Let's say we want to migrate PDB red from top to bottom, as shown here. We start by creating a refreshable PDB in the CDB to which we wish to relocate. Of course, this serves as a replica. I got ahead of myself here. This serves as a replica for DR purposes. If the top CDB fails, we can recover using the replica in the bottom CDB. When we're ready to we execute a switchover. So the associated role transition achieves the desired result. The PDB is now in the bottom CDB as a primary, and its replica in the top CDB can be used for failover purposes in the event of a disaster. All right. Next topic, real application clusters. And multi-tenant is closely integrated with real application clusters, also known as RAC. RAC, of course, is an architecture that provides great scalability as well as great availability. And in this section, we'll see both of these themes. Let's start by setting up a basic 2-node RAC cluster for a single CDB. There's a single database instance per node in the cluster. And of course, storage is shared between the nodes. Now, let's think about the PDBs in this CDB. Here we see PDBs 1, 2, 3, and 4. And we begin by discussing the topic of affinity. In other words, in which node or nodes of the cluster is each of these PDBs open? Technically, the affinity of a PDB to a database instance in the RAC cluster is defined by opening the services of the PDB in that instance. But what about the other nodes? Basically, each PDB is visible in every node of the cluster. However, in nodes in which it is not open, it will be in mounted state, which is about as closed as you can get. And with this configuration, we've got a pretty nicely balanced cluster. However, in nodes, now these little resource meters here show a pretty comfortable load on each node. So far, so good. But now let's add a couple more PDBs to the cluster. We'll open PDB 5 in node 1, PDB 6 in node 2. And now our cluster's beginning to look a little overburdened with these resource meters now in the red zone. To address this problem, we'll expand the cluster. by adding an additional node running a third instance, instance 3. Now we can do some load balancing by redistributing the PDBs across the newly expanded cluster. This is a nice, simple process. In fact, it can be done either by using servctl or via SQL using an alter pluggable database relocate command. And the result is that once more we see a nicely balanced load across our cluster. So far, we've seen what's described as singleton affinity. In other words, each PDB is open only in a single instance and present only in mounted state in other nodes. It's also possible for a PDB to be open in more than one node, or even all nodes. For example, as we see here, PDB 8 is open in just these two, and we have uniform affinity of PDB 7. Now, in general, singleton affinity is a very good model to follow, as we shall now see. The tight integration of multi-tenant with RAC includes a capability known as per PDB lock domain. And this provides strong isolation of a PDB's data and locks to the node or nodes in which it is open. So as is shown here, with PDBs 1 and 2 affinitized to node 1, 3 and 4 to node 2, 5 and 6 to node 3, and 7 and 8 to node 4, we know, for example, that only the SGA of node 1 has any data or locks to do with PDBs 1 and 2. And therefore, we know that in the event of a node failure, Cache Fusion need not consider any data or locks for PDBs not open in that node. So the benefit is twofold. The affected PDBs recover faster in the surviving nodes, and the brownout experienced in other PDBs in surviving nodes is significantly shorter. To illustrate the high availability characteristics of a CDB cluster, let's see what happens when one of the cluster nodes fails. Here we see a 4-node cluster and 12 PDBs distributed across the cluster with singleton affinity. With admin managed services, this primary affinity would be defined by specifying the PDB as preferred in the node in which the affinity, in which it has affinity, designated here with a P. The A's designate the node in which the PDB is marked as available, and this is the node to which the PDB will fail over in the event of failure of its preferred node. For instance, PDBs 1, 2, and 3 each have preferred affinity for instance 1. To spread the burden of a potential node failure across the cluster, each of these PDBs is marked available in a different node, PDB 1 in instance 2, PDB 2 in instance 3, and PDB 3 in instance 4. The M represents the mounted state of each of these PDBs in the other instances. So what happens if instance 1 fails? Each PDB that was open on the failed node fails over to the designated surviving node. So here we've seen the close integration between multi-tenant and RAC. We've seen how a PDB's affinity to a node in the cluster is defined by opening its services there, and we can elastically adjust to changing workloads simply by changing that affinity of PDBs for load balancing purposes. Relevant to a high availability theme, we've seen how effectively the surviving nodes of a cluster can absorb the additional burden in the event of a node failure, with per PDB lock domains minimizing both the outage in the affected PDB and the brownout experienced in the surviving node. Wow, we've covered a lot of ground in a single session. It's not called a masterclass for nothing. We've briefly reviewed database architectures, our design goals, some fundamental enabling innovations. Next, we covered 3 important enhancements that deliver faster, easier upgrades. provisioning just keeps getting better. There are several enhancements to discuss in this category. Transportable backups eliminate an obstacle to pluggable portability. Mission critical deployments demand data guard, and the integration of multi-tenant with data guard continues to strengthen. And the integration with real application clusters and multi-tenant is outstanding, I think. Now, our mission as ever is to help people see data in new ways, discover insights, unlock endless possibilities. And on reflection, that's an excellent theme for this session. I hope that I provided you some insights that will allow you to see our database in new ways and showcase some of the features that allow you to unlock these endless possibilities. And so here we transition a little bit and look forward, because we've got a big event coming in Oracle Database land, which is Oracle Database World. This is a virtual replacement for Oracle Open World, and we're running this in your time zone on November the 2nd and 3rd of this year, so not long now. We have keynotes by our two executive vice presidents, Juan Loaiza and Andy Mendelsohn, 3 executive sessions, 33 general sessions. I'm doing one of them about autonomous database, and there are several others, so be sure to look at the content catalog. There's some great stuff there. In addition, we've got 24 hands-on labs. In a minute, Kevin's going to tell you some more about this. One of these hands-on labs is indeed about multi-tenant. And I'm going to be your host, and I strongly recommend that you join that. And Joe, who is helping here with Q&A, is also going to be your host. So please join us for that. We also have a large number of on-demand sessions. We wanted to cram so much into this event, and there just wasn't time. So the idea of the on-demand sessions is that you can watch those outside the scheduled time. And of course, all the general sessions will be recorded as well, so you can catch up with those. Plenty of highlights, all sorts of good stuff. At this stage, Kevin, I think I should hand over to you to tell us a little bit about the Live Labs environment. Here's one of them. Can I hand back to you, Kevin?
Yes. Thanks a lot, Patrick. Thanks a lot for this very, very in-depth dive into the multi-tenant world and the clones. There were a lot of questions, a lot of great questions. I think it felt like almost every minute there was a question. Thanks to Dom, Joseph, and Robert for responding to all of these questions. I hope all the participants in here, the attendees, enjoyed the session. That was really, really a great one. Just to highlight, so the next steps for everyone, try it out yourself. We recommend going on to Live Labs portal. You see the URL here, and try out the hands-on workshop. There's also another one that I can highlight, which covers new features in 19C, which also goes a little bit into this area, into the topics that Patrick presented. And yes, as Patrick highlighted, join Patrick again, actually, November 2nd, 3rd for Oracle Database World, where he will be the host for the hands-on session and where you can ask even more questions in case your question wasn't answered today. I see there are still questions popping up. I hope Robert, Dom, and Joseph have still time to answer them. Other than that, yes, thank you so much for joining us today. Thank you so much for Patrick joining us at his very, very early time, 5 a.m. it was. I hope you had like a good session here, Patrick. I think indeed all the attendees had a great session, judging by the amount of questions and the interest that was shown here. For everyone who's going into the hands-on workshop, if you have questions, use this email address to raise questions. Other than that, feel free to check out the URL in order to see what is the next upcoming masterclass going forward. And I would say thank you so much for joining. Thanks a lot again, Patrick. Thanks, Dom, Robert, and Joseph for being on the Q&A panel. Thanks for Selen and Charlotte for hosting the session. I hope everyone has a great day, and we'll talk to you soon in the future. Thanks a lot, and take care.
Thank you. Bye-bye.